So we are in part B of chapter 1, section 5. We just got done seeing some of the application work that you can do with linear algebra. And now we're going to continue to add to this little repertoire of skill sets. So for this section, I think what I'm going to do just to kind of serve as an aid, let me start with a very simple equation. Okay? So 2 times x sub 1 plus x sub 2 is equal to 0. Look, if you can even, I could have even wrote it as 2x plus y equals 0. Okay, same idea. Now, I want you to think about some possible solutions to this equation. Right, so some x sub 1, some x sub 2, such that when you do 2 times x sub 1 plus x sub 2, you do get 0. Well, I think one solution comes to mind immediately. If I choose 0 for x sub 1 and 0 for x sub 2, then of course 2 times 0 plus 0 equals 0. Right? Of course. This is this elaborate duh of a statement is what's referred to as the trivial solution in linear algebra. So the trivial solution. And of course, again, so it's trivial because of course, if you add up a bunch of zeros, you will get 0. The real question when we ask about the solutions to this equation, the real questions that we're asking in linear algebra is, are there any non-trivial solutions? Right? That's what we're interested in. So for example, if I let x sub 1 equal 1, and I let x sub 2 equal negative 2, well, 2 times 1 minus 2 also equals 0. Now, both of these are solutions, but this is more along the lines of the types of solutions that we are looking for, because we just it's just always assumed, of course, the 0, 0 is one of the solutions. Okay, so we're looking for non-trivial solutions. Okay, well, we are looking for non-trivial solutions to what exactly? So we're going to start with the equation ax is equal to 0, right? And of course, that means that some matrix A times some vector x, and that's going to be equal to some 0 vector. Now, when ax is equal to 0, we're going to give that a name. Okay, and it's a name that you're going to, again, you're going to need to place to memory. So we refer to this equation as a homogeneous equation, right? Or homogeneous equation. So a homogeneous equation is going to always be set equal to 0. An homogeneous equation is always set equal to 0. Now, we do want solutions to homogeneous equations, but as I mentioned before, we want non-trivial solutions to homogeneous equations. In other words, just like 0, 0 is kind of a duh statement, if I make x 0, then matrix times 0 will also equal 0. But again, that's not what we're interested in. So the homogeneous equation ax equals 0 has a non-trivial solution if and only if, ready? If and only if the equation has at least one free variable. Now think about it for a second. A free variable indicates multiple solutions, doesn't it? Right? Indicates infinite solutions. So, whereas if you have no free variables of a consistent matrix, then you would expect to only find one solution, a unique solution. So what that means is if 0, 0 is already one of your solutions, then in order to have any more, we're going to have free variables. So that is, in essence, what this question comes down to. Can we find at least one free variable? If so, we should be able to find non-trivial solutions. Let's begin. So the first question, and I'll read it in its entirety because a lot of times, again, in linear algebra, it's just understanding what you're supposed to do and when you're supposed to do it is the hard part. So the question reads as follows. Determine if the following homogeneous system has a non-trivial solution. So this, of course, is a system. And because it's already set equal to 0, it is a homogeneous system. Now, we want to determine if this system has a non-trivial solution. Now, once we do determine that, then we want to describe it. But for right now, how do we determine if it has a non-trivial solution? Well, I've already mentioned this. The real question that you are asking yourself is, are there any free variables? Okay? That we need a free variable to have hopes of having more than one solution. And we already know one solution, right? If you chose 0, 0, 0 for x1, x2, x3, then that is, of course, one solution. But we want non-trivial solutions. Ready. So how do we do this? Well, it does. So I'll go ahead and write. So we're going to start with the AX is equal to 0 equation. And again, structurally, we're looking for x equals, right? What we have is A, or what we will have is A, and 0. So let's go ahead and, right now, let's form a matrix. We can go right to a matrix from this system. So we have 3, -3, 6, 5, -2, 1, -4, 4, -8, and of course you have 0, 0, 0. Okay, so notice we could go right from that system to that augmented matrix, which is a 3 by 4 matrix. Now, as soon as we're here, we can use that row reduction algorithm, right? We can RREF. And then let me go ahead and do that. So this is the result from that row reduction. And we got 1, 0, 0, 0, 1, 0. Now, so far, there are no free variables, right? Pivot here. That means basic variable here, basic variable here. It's going to depend on what this next column is. Because if we get another, say, 0, 0, 1, well, we don't have any free variables. But this is what we should be getting for that third column. Negative 4/3, 0, 0. So notice that x sub 1 is a free variable, x sub 2 is a free variable. I'm sorry, my apologies. X sub 1 is a basic variable, x sub 2 is a basic variable, but notice that x sub 3 is the free variable. So let us go ahead and write. We went from system to matrix just so our calculator could do the lifting. And now let's go from matrix back to system just so that we can interpret the system better. So what we have is x sub 1 minus 4/3 x sub 3 equals 0, right? That first row translates to that first equation. That second row translates into x sub 2 is equal to 0. And of course, that third row translates into the third equation, 0 equals 0. All right. Now, at this stage, if you wanted to determine whether the following homogeneous system has a non-trivial solution, at this stage right now, you could point out that, my apologies, I don't know why I marked through my matrix, but I'll have to rewrite it. Bear with me. So 1, 0, 0, and that was 0, 1, 0, negative 4/3, 0, 0, and finally 0, 0, 0. Okay, so my apologies. So now that we have determined that there are free variables, we can answer the question, since the system has free variables, then it has a non-trivial solution. But it also asks us to describe the solution set. And as far as, or at least the way I would start thinking about this is we're just going to continue to write it in the general form of the solution. And of course, with the general form, that means we solve for our basic variables. So x sub 1 equals, we got to bring that negative 4/3 x sub 3 to the other side. And we always state which variable is free. So it looks like this. X sub 1 is equal to 4/3 x sub 3. X sub 2 is actually just 0. Okay, x sub 2 is equal to 0, but x sub 3 is free, is equal to free. It's fine. All right, so that is the way we would interpret the general form of the solution. Now, I'll say a couple quick things. Just thinking back through the years of teaching this class, remember a trivial solution is all zeros. So just because 0 shows up here for x sub 2, that doesn't mean it's trivial, right? Trivial would mean that all three variables are equal to 0. Okay, but let me pose some questions, and then we're going to look at the geometry of this work, because 1.5 doesn't have a lot of questions, so I want to make sure that we get the most from our questions. Okay, so what if I were to follow up this question with which value I'm just trying to figure out how to word which value of the free variable, right, yields the trivial solution. Now, this follow-up, or say part B to this question, is so easy of a question, but I can just imagine the language tricking a student. So it's simply asking, what should the value of the free variable be so that when you plug it in, you get the trivial solution? That's really what I'm asking. Right? So the trivial solution is 0, 0, 0. Well, of course, if you let x sub 3 equal 0, right, wouldn't that be required? If you let x sub 3 equal 0, well, x sub 2 is already 0. And now if you take x sub 3 and take that 0 and plug it here, 4/3 of 0 is also 0. So that's a fairly easy question. Let me now show you one. Let's say there was a part C to this question. Again, I will do my best with the language here. Describe vector x in this system. So vector x in this. So let's think about it as since x sub 3, let's see if I can, the best way of trying to describe this to you. Yeah, let's think of it like this. So if I come, I'm gonna kind of go from here. So when you start to think about the vector x in this system, the way you want to think about it as x sub 3, the free variable, is a scalar that's attached to some vector. When you think about that, if you were to, let's see if I can try to explain it this way. This is kind of sloppy in its language, but if you were to factor out an x, if you were to factor out an x sub 3 out of this general form, let's think about what would be left. So if you factor out an x sub 3 here, then do you with me that all you would be left with is 4/3? Now, if you factor out an x sub 3 here, well, which is just 0, right? So there's really no way to, it's just still 0. And of course, it doesn't really, since x sub 3 is free, if you factor an x sub 3 out of an x sub 3, you're left with just 1. So this is the vector that is being scaled by this free variable. Now, I want to show you the geometry of this, because I can imagine that, well, maybe there's a student that followed me all the way up till I got to here, and then that was a little bit maybe esoteric, or maybe it was a little bit worded, and could have been worded better. But ready? Let me see if I can now try to explain what's happening. So what do I mean by this vector v? Well, now imagine, so since vector v is equal to 4/3, 0, 1. Again, for my engineer students, imagine 4/3 I plus 0 j plus 1 k, if that helps. But this, if you were to graph, that would be vector v. Okay. Now, when you choose something for your free variable, what you're doing is you're scaling this vector. So does that make sense that if this is v, if you were to choose 2 for x of 3, then you would get 2v, right? You would have doubled the size. If you would have chosen -1 for x of 3, you would have gotten same vector in the opposite direction. Now, do you understand that every point on this line is simply this vector scaled by whatever you choose for your free variable? You can reach any point you want on this line by just choosing a different scalar, choosing a different value for your free variable. Now, all of these points, right, will make this system equal 0. So I don't know what this point is right here. Right, if this is 4/3, 0, 1, I don't know what point this is right here, but I'm telling you, whatever it is, whatever the x sub 1 value is, x sub 2, x sub 3, if you plug it in, x sub 2, x sub 3, you will get a non-trivial solution. So that's what they mean by the span of vector v. There it is. Every single solution. Look, up here, one more time. There's a whole, what are all the solutions that make this linear system true, right? All the different x sub 1, x sub 2, x sub 3 combinations, well, they're all located here on this line that just happens to be the vector v scaled by x sub 3. Okay, so let's take a look at example 2. And I'll try, I think what I will do for example 2 is, well, let me see if I can pick up the pace a little bit, but I do want to show you the geometry. Ready? So it says, example 2, a single linear equation, which is what we have here, can be treated as a very simple system of equations. Okay, now, we want to describe all the solutions of the homogeneous system. Now, homogeneous because, right, it's set equal to 0. And we're looking, we know that the trivial solution is one of those solutions, x sub 1, x sub 2, x sub 3, but is it the only one? Or in other words, are there other solutions out there that you could plug in for x1, x2, x3 to get 0? Well, how do we know? Well, we'll see if we can figure this out. The way you would set up a matrix for this, very, very simple matrix, right? Because it's only one row, isn't it? You got 10, -3, -2, 0. So this is a 1/4 matrix. Now, I don't need to even RREF this matrix to tell you there is free variables. Think about it for a second. How many variables do you have? Look up here. You have 1, 2, 3 variables. How many equations do you have? You have one equation. You have more variables than equations. So in terms of, there can only be one pivot, right? There can only be one pivot for this, which would be located here. So this x sub 2, x sub 3, these are going to be free variables. I don't even need to REF, but I am going to do it anyway. I think so. Actually, no. What I'll do, it's even simpler since it's only one equation. What I'm going to do, this is so simple, I'm just going to solve for x sub 1. All right, so we get this negative 2x over here, we get this negative 3x sub 3 over here, and then we divide by 10. I'll just write it. I'll do it in 2 steps. So 10x sub 1 is equal to 3x sub 2 plus 2x sub 3. And then I'll divide by 10, divide by 10, divide by 10. So x sub 1 is equal to, 3 tenths or 0.3 x sub 2 plus 2 tenths or 0.2 x sub 3. Okay. Do you see? One basic, 2 free variables. General solution, x sub 1 is equal to 0.3 x sub 2 plus 0.2 x sub 3. But hey, what do we say about x sub 2 and x sub 3? Yeah, we have to make a statement about them. We have to say that they are free. They are free variables. So we would be free to choose whatever we want for these guys. But once you do, we're going to take a break. I'll just drop this before I, I'll just drop this on you before I start the next video. So take, for example, the point 23, 10, 100. X sub 1, x sub 2, x sub 3. Is that point a solution to this system? Okay. And then we'll try to figure out, how do we think about the vectors? How do we describe the x vectors? Now, I'll go ahead and take a break, and we'll finish up 1.5 in the next video.